Welcome. This is an example problem about density. A hollow cylindrical copper wire is 1.5 m long and has an outside diameter of 3.5 cm and an inside diameter of 2.5 cm. How much does it weigh? Let's write the given data. Your L is 1.5 m. The outside diameter is 3.5 times 10 negative 2 m. And we might as well have our outside radius. For reference, your inside diameter is 2.5 times 10 negative 2. And your density, copper's density, the one that we mentioned before, 8.9 times 10 cubed. By definition, we know that weight is equal to mg. And we don't have any m. We do have a g, but we don't have any m. So if we remember, our raw density is actually equal to your m all over our volume. So it's not velocity. A lot of people say that it might be, but it is not. This is just mass all over our volume. Now, given that, because this is again the shape is really important here. Hollow cylindrical copper pipe, and we must understand how, because our density is already given. We don't have any mass, and the way to get the mass is by knowing the volume. Now, the volume of the hollow cylinder is given as pi multiplied to your change in radius squared, or R2 minus R1 squared, times your L, or your length. Now, simplifying or substituting, that will just give us V is equal to the pi, and R here, it should be the outside first, so that is 1.75 times 10 negative 2 times 10 negative 2 squared minus, I'll put it right here, minus 1.25 times 10 negative 2 squared times our L, which is 1.5 or 1.50 meters. That'll just give us 7.06 times 10 negative 4 cubic m. Then that volume can now be used to get our m. So from this, we can have m is equal to your raw density times our volume, which gives us this data, that is 8.9 times 10 cubed times 7.06 times 10 negative 4. That gives us 6.29 kilograms. And from there, we can use that to get the weight, which is give us weight is equal to my 6.29 kg times 9.8. That is your acceleration due to gravity, which gives us 61.7 newtons. We're going to be talking about pressure in the fluid, and we have here a two-part problem. Scientists have found evidence that Mars may once have had an ocean 0.5 kilometer deep. The acceleration due to gravity in Mars is 3.701 m over s squared. Letter A. What would be the gauge pressure at the bottom of such an ocean, assuming that it was fresh water? And letter B. To what depth would you need to go in the Earth's ocean to experience the same gauge pressure? Let's have the given data. We've got here the depth, 0.5 km. So let's just name it as depth. 0.500 km. Acceleration due to gravity. Let's call it gm, which is gravity on Mars. That is 3.71 m over s squared. Letter A. This is letter A. What would be the gauge pressure at the bottom of such an ocean? If we're looking for gauge pressure, we might just have gauge pressure is equal to our raw density times your gravity on Mars times your height. In this case, our depth. Okay? That would just give us, according to the raw density table, we have 1,000 kg. This is just given. Same is true with your g, which is 3.71 in this case. Your height here, instead of 0.5, that is just 500 meters. Calculate. We actually have 1,855,000 Newton per meter squared, or pascals. Letter B, to what depth would you need to go in the Earth's ocean to experience the same gauge pressure? We're looking for the depth. And previously we said that our depth here was noted by S. And here it is. Okay. So a while ago, we just solved that gauge pressure is actually 1,855,000 pascals is equal to our formula a while ago, which was raw density. G a while ago was Mars, but this time is Earth times your height. In this case is your depth. So we're actually looking for the H right now in terms of Earth, in terms of the Earth's surface. So having everything into consideration, we just need H is equal to your gauge pressure all over our raw density, 1,000 kilogram per cubic meters, times my gravity, which is 9.8 on Earth. Your gauge pressure is just 1.86 times 10�3 to the 6th power. So just plug it in there. Just give us approximately 188 or 189. So let's have 189 meters. The topic is buoyancy. A 950 kilogram cylindrical can buoy floats vertically in salt water. The diameter of the buoy is 0.900 meter. Calculate the additional distance the buoy will sink when a 70 kilogram man stands on top of it. Let's take a look at different given. I've got here the mass of, the mass of the cylindrical can 950 kg. I also have the diameter 0.900 m. Calculate the additional distance. Let's have a dia, and we're looking for distance. 70 kg man. So there's another mass here. The man, 70.0 kg. On top of it, we know that the density of seawater is given as raw 1.03 times 10 cube kg all over cubic meters. Now we have the diameter, we can also have the radius, and we can see that nothing must be converted here. So we are looking for the additional distance. So that is just D, the additional distance. How would we get it? Firstly, know that the buoy is equal to the weight of the man. The buoy is equal to the weight of the man, knowing that the weight is just mg, and the buoyancy formula is just equal to your raw density times your gravity times your volume, we can definitely see where we can get our D. So I have a G here and I've got G there. That'll just give us raw gravity, raw V is equal to our M. Okay, V here is additional volume displaced when the man decides to stand on the buoy. Our V here is also equal to our AD. V is equal to area times the distance. So we know that the distance is what we need. What do we need, or what do we need to do with the area? So from here, I can just remove my my V and just have it in terms of my area distance, but area in terms of my radius. So because we have our diameter, well, it can be in terms of your diameter as well. So in this case, that would just be raw, copying the raw, times pi r squared, that is your A, and my D is being copied, is equal to M. We're looking for D. So just copy this, put it there, that is just D, is equal to your M, all over your raw, pi r squared. Pi r squared. Substituting, my M is just my M is just 70. Is it 70? Yeah, 70. My M is just 70 kg. Kg. My raw is 1.03. Just leave the units for now. 70. 1.03 times 10 cube. Okay. Times our pi. And our r squared. Basically, if your diameter is 0.9, then your r must be 0.450 m. So that must be 0.450. Okay, multiplying everything, we'll just have 1.03 calculating everything, we'll just have 70 times, divided by 1.03 raised to third times our pi times 0.450. We have 0.048, 0.048, and that would just be in M. Or 0.041, and that will be our height. This is about buoyancy. A slab of ice floats on a freshwater lake. What minimum volume must the slab have for a 45-kilogram woman to be able to stand on it without getting her feet wet? Let's see. Firstly, let's take a look at our given data. What minimum volume? We're looking for the volume minimum for a 45-kilogram woman to be able. So we have M, woman, which is equal to 45.0 kg. We're looking for the minimum volume of a slab. So, by definition, we all know the equation for buoyancy force of water is just equal to force, buoyancy, equal to rho, volume, and your gravity. Remember that this is for water, the buoyancy force of water. Now, if we're looking for the total weight, that must be W is equal to mg. That's it. However, there is such buoyancy, which is again rho times volume times gravity. So I can just put here rho times volume times gravity. And we know that the rho of the density of your water is just 1,000 kilogram per cubic meters. And the density of ice, H2O solid, is just 1,000 kilogram cubic meters. Density of your H2O. Oh, I'm sorry, this is liquid. Okay. Liquid, and this is solid, which is ice. That is just 0.92 times 10 cube kilogram cubic meters. And the mass of the woman is 45 kilograms. And we've got to have a G, gravity, and we must have the volume as well. Now, since buoyancy force is just equal to total weight, we'll just use this one, these two equations here. So your force is just rho. Yes, rho, and then volume times gravity is just basically equal to, this is for water, let's just put liquid, which is equal to rho, volume, gravity. This is solid plus your mg. This is just your weight. So this is boy plus weight. And rewriting it to get the volume, let's just have a volume is equal to m over rho liquid minus rho solid. It'll give us 45 kg all over 1,000 minus 0.92 times 10 cube. That should be 0.5625 cubic meter. And that is your minimum volume, or that should be the minimum volume of this lab. So the woman can maintain her ground without her feet getting wet. Our topic is fluid flow, and this is one of the problems I answered for you to practice. A shower head has 20 circular openings, each with a radius 1 millimeter. The shower head is connected to a pipe with a radius 0.8 cm. If the speed of water in the pipe is 3.0 m over s, what is its speed as it exits the shower head openings? As you can see, this is a fluid flow problem. It only means that the continuity equation must be used, and we can see that the fluid is considered incompressible. Now, let's identify our equation. Our equation for continuity for an incompressible fluid must be change in your volume in terms of time is just equal to your area, 1, times your velocity, 1, equals area 2, velocity 2. So the first part of the equation is just the volume flow rate of a liquid. The next is the speed flow, 2 points. So from 1 to 2. And the area is just a cross-sectional area of a tube. Now, it says here that the shower head has 20 identical openings. And it has the same speed and area in each opening. Now, let's just say that the area that we're looking for is given as area equals pi r squared. Pi r squared. And because there are 20 openings, we can say that n is just equal to 20. Now, since A1, V1 must be equal to A2, V2, I can therefore just attach my n in the equation, making it look like n A1, V1, which is my velocity, equals A2, V2. And I'm going to be needing what is its speed as it exits the shower head openings. We're looking for the speed. So solving the equation, so I can get my V1, that will just be V1 is equal to my A2, V2, all over my A1, but in this case, we've got my N A1. My A2 is just pi r squared, as we just mentioned here, pi r squared, times our velocity. Our velocity squared, excuse me, V2 here. So that is 3.0. Three m over s. Yeah. Next is my n being 20, A1 is pi r squared 1. That is just it. So my pi is given, it's 3.14. My R2 is 0.8 times 10 negative 2. So I'll just times 0.8 times 10 negative 2 squared times 3 all over 20, 3.14. My pi is 3.14. My r is 1. So 1 times 10, negative 3m squared. Times 1 is 10, negative 3m squared. Okay. That'll just give us 9.6 m over s, which is for our v, or velocity, speed as it exits the shower head openings.